Welcome to the Amphigory Effect podcast with your host, Zach Brackett, and your co-host, Justin Marlowe. Let's begin.
Hey everybody, welcome to the Amphigory Effect podcast. Today we are at York Technical College in Rock Hill, South Carolina. And Justin, who are we sitting here with today?
Today we're here with my physics professor, Mr. Jose Cardoza.
Hi.
Tell us a little bit about yourself.
By trade, I'm an astrophysicist. I've been at York Tech for about 5 years now,
Okay.
and I teach introductory level physics courses and astronomy classes here.
Wow, that's awesome.
Yep.
Okay, I told him before we started shooting that I will represent the people who know nothing about physics because I don't know anything about physics. So I'll be asking you a lot of stupid questions, and we'll all learn together today.
No question is stupid.
That's what I like to
Yes,
hear. That's what I like to
I
hear.
know just enough to be dangerous is what I've been told. So.
All right, so let's get into what is quantum mechanics? What is quantum physics?
Okay, so the basic idea of quantum physics is the study of matter at the atomic level.
Wow, so really small stuff.
Yep, that's
Okay.
it. It is a theory on how matter behaves at those sizes that are essentially atom-like, so nanometers, angstroms.
So why does that distinction between quantum mechanics and just physics need to be made? I think a lot of people don't understand what really is going on there.
Sure. So theories in general, they all have limitations, right? So for example, in physics 1 even, or in our everyday experiences, we know that if I drop this, it's going to fall straight down, right? And this accelerates at the same rate, 9.8 meters per second square, right? And you can use Newton's laws of motion to say if I start here and I know the distance that it's traveling, how fast it's going to hit the ground, right? And I apply my motion, my kinematic equations. But I take this. That does not accelerate at the same rate, right? There's a limitation to that.
Okay.
Because in the assumption of dropping this object is we're assuming that we can treat this as a point particle, right? And that we can ignore what this has, which is air resistance.
Okay.
Okay. So there's a limitation there where the theory breaks down. Well, quantum mechanics it's that. It is a theory that works at the small level because other theories don't work well in that regime. A famous theory is general relativity, right? General relativity does a fantastic job at explaining how the universe works at the large scale, right? So black holes helps to explain that. It helps to explain the warping of space and time by mass, right?
Okay.
It helps to explain phenomena that you see, for example, if you look at some astronomical objects, warping of space and time, for example, is if I have something here and I put this on my left eye, I won't see it, right?
Right.
Because I'm seeing the light that's being reflected by this, right? And right now, that light that's being reflected is being absorbed by that, and I can't see it.
Okay.
So warping of space-time says, look, well, this object has a mass. Imagine that this is a very distant star and that this is a galaxy, for example.
Okay.
The fact that space is warped by matter means that if I do this, I can still see this. Because when that light comes this way, this matter warps space so that this light can travel around. So it can travel around. And normally what you see with these objects is you end up seeing something that's like a cross.
Okay.
I won't see the object. I'll just see a little dot when you're looking at this at these distant stars. But you'll see 4 little dots. So I'll see one on each because light warps to the left, to the right,
Oh, I see.
above,
Okay.
below, and you get this cross-like pattern. So general relativity works really well at the large scale, and when you apply general relativity to the quantum world, it just gives you bad answers. And what are bad answers? A bad answer would be the probability of something being negative, right?
That does seem like a problem.
That is a bad answer. If you say, oh, the chances of being here is -4,
Yeah.
what does that even mean, right? So that's an example where the theory just breaks down. So you need modifications. You need, and in this case, not modifications. You need a completely new theory, and that's what quantum mechanics does. It looks at explaining matter at those small scales.
Wow. Okay, that blows my mind a little bit.
A little bit.
Yeah, I had never known what quantum mechanics. I assumed it was some small stuff because quantum.
Yeah.
But that's really cool that you have to make up a whole different theory just to explain the things that are happening at that level.
Absolutely, and that's kind of one of the holy grails of physics, is to try to get one theory that can explain everything. If you do that, you will be the most famous person that has ever lived, and perhaps will ever live.
Yeah.
Because
that changed everything then.
Yeah, if you can get one theory that can explain all of this, and I mean all of the phenomena at the atomic level, all the phenomena at the level of, galaxies and superclusters, and the expanding universe and dark energy. If you can do that,
wow,
then you are
Yeah, that's crazy.
Sounds like a tall order.
Yeah, for real. Someone's got to step up to the plate, right?
Gonna be me.
Won't be me.
Please do.
Somebody has to do it.
Okay, so when I think of physics, and I guess this goes to the quantum level too, and I'm interested, we talked a little bit before, I've done a little bit of research into the many worlds theory, right, where there's multiple universes and things like that, because that interests me. But how does that work with quantum mechanics or quantum physics?
So let's go a little bit into how that comes about, the many world interpretation. And its origin, believe it or not, is in astronomy, in astrophysics.
Okay.
And it comes out of the idea that when the universe first began, we all come, you hear phrases like, oh, the universe started with some undefined point. And how did it get started? A quantum fluctuation. If you look things up, things started with a quantum fluctuation. Right?
Okay.
The Big Bang started with that. So the Big Bang theory does a pretty good job at telling people, or telling physicists, what happened after the universe started, right?
Mm-hmm.
But it doesn't really do a good job at explaining why did the Big Bang happen, right? And how do you explain the formation, and how do you explain certain phenomena that you see in the universe, like the fact that if you look out in space, everything looks pretty much the same, right? And furthermore, if you take a temperature of space, and you can take a temperature of space, the cosmic microwave background radiation, when you do that, you see that it's pretty much the same everywhere.
Really?
Mm-hmm. And so one of the implications of that is that if it's the same everywhere, then how did that happen? It tells you that things sort of had to be together and expand. That's what the Big Bang, that's something else, the expansion of the universe. But how does that information that everything should be the same get communicated, when, if you compare things that are on the opposite side of the universe, the time required for any signal, and as far as we know, all signals cannot travel at the fastest they can travel is the speed of light.
Right.
When these objects are separated by things that would require, a travel of 10 times the speed of light or something like that. Okay. So when you look at that, it comes out of the idea that the universe went bang, and that's a whole nother thing. But in the theory that describes, which is called inflation, how the universe got to where it is, part of that theory has in it that if that happened in the space, right, if we came back to a location, whatever that caused, that quantum fluctuation, whatever that is, the theory says that bang can happen in other spaces, and it can happen multiple times.
Right.
And that every time that thing goes bang, that is the beginning of a new universe.
Oh, wow.
So we have the idea of the multiverse,
Mm-hmm.
the multiverse coming from that.
So would these kind of fluctuations, would that be detectable if it was in our universe, or is this something that would be outside of our universe?
Well, right now, if you look at light that's coming from the past, right? Because when we look out in space, since light takes time to get here, right? A signal had to be sent a certain amount of time before it got to us, right? So if this is the fastest something can move, right? It just took 1 second, right? Let's just say 4 seconds to get here. So I'm looking at this as it was 4 seconds ago.
Oh, I see.
With the universe, you're looking at things that are 13 point something billion years ago. The light that people can see, I think, goes back to a few seconds before the Big Bang. Don't know exactly the number, but you cannot see to when exactly it went Big Bang.
Oh, I see. Okay. So
So you can go to fractions of seconds. Let's just say that much. That much is, but beyond that, we haven't seen that. So you can't see when these quantum fluctuations, and plus you only will be able to see what's in this universe anyway,
Right.
right? Because if we've expanded, right now, most scientists believe there is no interaction happening between these different universes. People are looking for that telltale sign of an interaction between different universes.
Wormholes or something.
Well, what they're looking at are what would happen if two objects collide. If two objects collide, the idea is that there will be ripples sent as the collision happen with these two universes, and you'll be able to detect those ripples. That's an idea of trying to prove that there is a multiverse, because that's still a theory, so there isn't any proof of that. And if we were to look and see stuff from the other universe, we can't, because it's so far away. It wouldn't be able to reach us right now, right? Because it's traveling at the speed of light, and given our expansion, we can only see back in time 13.7 billion years, more or less, which means that light that was emitted 13.7 billion years ago.
Oh, okay. I see.
And so something that's outside of our universe, well, first of all, that's just a theory. And outside of our universe, it's just a theory to begin with. But we wouldn't be able to see that because we're expanding. And our acceleration is not just linear, it's an accelerated expansion.
So are there assumptions of how other universes would behave? Are we comparing them to our own? Or are we, how does that work?
Sure. So, well, to be honest, no one has an idea of how it behaves.
Right.
But there are some clues. There's some clues when you begin to look at the constituents that make up our universe, right? And so what makes up our universe? Dark energy has been found. It's a huge constituent that makes up our universe, right?
Now, what is exactly dark energy?
So let me finish with the other two.
Okay,
so
fine.
So it'd be dark energy, dark matter,
It's a rabbit hole.
and quote regular matter. Let's call it that. So let's
I think I know the last one.
Yeah, that's
You'd
true.
be surprised. Wait, let him keep talking.
Yeah. So those are the constituents that make up our universe. So, and I'll go into a little bit. So what is dark energy? So dark energy, well, people don't know what dark energy is, but people know the effect of dark energy. So dark energy is a term used to describe what causes the acceleration in our universe.
Oh, I see. Okay.
So that is what dark energy.
So we see the effect. We don't actually know what it is.
Right.
Okay.
Oh, we describe the effect by calling it dark energy. Correct.
Ah, I see.
Yes.
I see. Okay.
But what is it? Don't know. Because first of all, if we start looking at some of the laws of physics, the laws of physics as we know it works really well when describing regular matter. Dark matter, dark energy. That's new stuff, so we don't really know how that works. But if you think about it, if the universe is expanding, right, and dark energy is the cause of that, and it's dark, that thing that causes the universe to accelerate, where is that coming from? Right? If it's energy that's coming into our system, where is it coming from? I thought our universe was everything.
Yeah.
So it's coming from somewhere else. And so people, where is that somewhere else?
Oh, I see. Okay.
Another universe? wow, that's strange. Another universe is giving us energy. Whatever that other thing is, don't know where that is. So that's what that is. So when you look at the multiverse, to answer your questions, and a lot of the ideas of what that is comes at looking at the parameters that define our universe. So the amount of dark energy, the amount of dark matter, the amount of regular matter. But it's not so easy, because the amount of dark energy really causes things to work in a certain way. So if you can have too much of something at one point, you produce different universes. So for example, if you look at something called the cosmological constant, right, which tells you the rate of which the universe is expanding, right? If you change that, if you tweak that parameter, which is a parameter for our universe, so it should be a parameter. It could be a parameter for another universe, right? If you tweak that just a little bit, then you can get universes where the expansion was so fast that you never gave the universe the chance for regular matter to form. So you never gave the universe the chance for electrons and atoms to form.
Okay.
Because it expanded too fast. You didn't give it enough time for energy to, quote, cool down. Let's say that, cool down and form regular matter. So you can have universes where no regular matter exists.
So it would be just dark energy and dark matter then?
So it could be, yeah. So it could be, or something else that we don't know about. Yes.
Wow.
But what that means is, the idea of the multiverse is, even if we have the same parameters of what we have, things could be anything that you want. So a good documentary on this is Brian Greene's documentary on the cosmos. So he has different parts. What is time? What is and so he kind of gives you this idea of that. But you can have a situation. So if there's an infinite number of these, then what does another universe look like? You can answer that. What do you want another universe to look like?
Oh, I see what you're saying. So I can
all the people are corgis.
Yeah,
sure.
Yeah. So that's it. Or a completely parallel where,
sure,
everything is exactly opposite.
Sure.
Right. Okay.
Whatever
that's
you
fun.
want. Yeah, it's an infinite number, right?
Yeah.
Infinity is that.
But here's my question with the multiverse theory is, with a scientific theory, you want to explain something, right? You want to come up with a reason that something happens. What does another universe that doesn't interact with ours explain?
What does another universe that doesn't interact with explain? Well,
is that not just a dead end? Like, oh, there's other universes, but what does that actually mean for us?
That's I see what you mean. That's a lot of times, that's sort of a debate that you get a lot of times between an experimentalist and a theorist. An experimentalist will say, why do I care if this is just a theory? Where's the proof? And I can't even find the proof because I can't interact with other universes.
Right. So why waste my time?
What's the point of this? Well, a theorist will say, just because you can't find it or prove it doesn't mean it doesn't exist. And the theory that describes this multiverse, right? You shouldn't just throw it out of the, throw it out because you can't prove it, when you can use that theory to explain other phenomena here.
Oh, I see.
And so the idea of the multiverse comes from theories from inflation, in part from inflation, the implication of inflation. And inflation works really well at explaining our universe. It explains why the universe is the way it is. And one of the key things is that the idea inflation really tells you, why was it that the universe is as large as it is? And so it says that there was a short period of time where things just exploded. So you had something the size of an atom, right, growing to the size of a galaxy in something like a billionth of a billionth of a billionth of a second.
Oof.
So, right. And you need that in order to